Okay, so we're starting here at about 8:05, and we're going to go over this in a relatively quick fashion here, at least the first few slides. And if you have a question, please interrupt. Okay, this isn't meant to be, a lecture where you just sit without, interacting or anything like that. I encourage you to stop me and to ask, anything that's on your mind here. Okay, so we started out with calculus. Calculus deals with a lot of things, but two central concepts or questions that you have in calculus is how fast is something happening or how much has something happened. And so we have these two terms that are perhaps familiar to you, but maybe not, but maybe you don't know the definition precisely. We have the derivative, which basically deals with rates, okay? Things, how fast are you going? How much is something changing? How fast does one variable change with respect to another? Things of those kinds of questions. And then the integral is how much. For example, if you're traveling at a certain speed, how far did you go after a certain amount of time? So we're going to deal mostly in this course with the derivative, although we're going to get to the integral at the end of the semester. So when we're talking about how fast, if you remember in algebra, you talked about the slope of a line, which really is an indication on how fast y is changing with respect to x. And so we calculate that slope as the difference of the y's divided by the difference of the x's. So if you have a large m, a large slope, that means you have gone up a lot versus increasing x by a little bit. And so we have this concept of a slope with a line. But what we're interested in, just like when you're driving in a car, you don't always drive at the same speed. You may vary your speed. We have functions that vary in value. And so we're interested in the rate of change, but the rate of change, as a matter of definition, gets to be a little fuzzy. With a line, it's very clear. You take any 2 points and you'll get the same slope. In fact, that's a pretty good definition of a line, is that the slope never changes. With a curve, you can see here that if you choose 2 points, you might get different slopes, and nothing really corresponds to a particular slope at a particular point. So we have this concept of a tangent line, and so we're going to choose the point that we're interested in finding the slope. And we're going to draw a straight line so it just touches at one point. And in this particular diagram, the point P is where we're interested in the slope, the value of P for y equals x squared. If x equals 2, y equals 4. What's the rate of change of y at that point? So first we have to ask ourselves, what are tangents, in the sense that we have this notion that it only touches in one spot, or maybe has kind of the same slope, but we have to kind of get a little bit more specific about what we mean by a tangent. And so Monday we went over these 6 points, and we decided which ones were tangents and which ones weren't, based on more or less an intuitive feel. A was not, B was not, C was, D was, E was, but F was not, okay? So it's this notion that you want to just kind of skim along the curve. At point D, you can go through the curve because it changes the direction in which it's curving, which is fine, but we don't want to intersect the curve like we do in B, where we go through it and we really don't have a line that's in relationship with the curve in any other fashion than just the intersection. So one of the things that I like to think about visually is, imagine you have a shape that you're going to put on a flat surface. It would touch at one point, and so if you were to somehow turn this thing over and touch C to a line or a table or something of that sort, you would have this one point of contact, and that's a good way to think about slope. That if you moved it at all, you'd get a different point of contact. All right, so we went through and decided on which ones were the positive and negative slopes. We have, as a negative slope, we have C, we have F, and in the positive slopes, we had A. My handwriting's pretty lousy here. A and D. And then the slope is the greatest at A, and it would be the least at F. Okay, so when that slope is going down, that's even though the size of the number, you know, it would be a fairly steep slope. We're negative, so we talk about slope as the value of it as being on the number line, where the more negative you get, the smaller the number. So we talk about A being really a high slope, F as being a really low slope. The numbers of these things, of course, can be anywhere. We don't have any scale on these yet. Okay, so then if we start assigning some numbers, and let's just say that I know that these values are associated with this curve. The -3, that's a fairly steep negative slope, and we look through all of them, and we can decide that perhaps B is the slope that is the most negative. Another negative slope, which is a little bit more gentle, okay, would be C, would probably correspond to that -1. The places that we don't have a particular slope, and maybe, yeah, okay, we look at A. I needed to take a closer look. And you see A, it's like at the bottom of this valley where the slope was negative until it gets to A, and then all of a sudden the slope is turning a little bit positive. So we have these slopes where when the tangent line is a horizontal line, that we say the slope is 0. Now your positive slopes, we look at A, or excuse me, point D as being a fairly gentle positive slope. So we'll assign that the value 1. And then the steepest slope in there, of course, is E. And so E, if it has a value that's recorded here, would be 2. All right, so in the homework you had some exercises like this where you had to determine where is or what does the slope, if we were to make a continuous curve that would describe the slope at any point, what would that continuous curve look like? And so we can pick out certain points, like if we look at maybe this point down here and this point up here, you can see that would fit that definition of a 0 slope, you know, where it's going either from a positive to a negative slope or from a negative to a positive slope, and at some point, if we draw our slope line, it'll be exactly horizontal. So it's probably the best place if you're going to sketch a graph to start, because you know that these things intersect the axes. And so what I'll do is I'll maybe make a little dashed line down to the 0. Like that, and then another dashed line that goes down to a 0 here. And so that would be the points that would be, you know, the easiest ones to determine precisely, because we know 0 is 0, and there's where the axis is. Now, the next thing that we can probably ask ourselves is in between those points, are they positive or negative slopes? So if we look from this place right, let me get my pointer straight, right there, up to the point where it's at its maximum, up to right there, everything in between that is a positive slope. Now the slope changes a little bit because it's curved, and in fact it changes as we're approaching that peak. It's at its kind of a low value for a positive slope, right? It's a very gentle slope. Think of yourself climbing a mountain with that profile. You know, you'd start out really, really steep, and then it'd be less steep as we get to the peak. So this graph would probably start off at some point, and maybe the slope would be the same, but it would absolutely go down to the point where the slope would be 0 as you get to the point where the slope is exactly 0. Now the same thing in the next segment, we have a negative slope. It starts off with kind of a gentle negative slope, it gets to be a steep negative slope, and then it kind of tapers out. So we'd expect that graph to look like this. So somewhere in here you'd have this maximum slope that you would find maybe halfway through that descent. And then of course we would get to be positive again as the function increases. Really close to that zero, it's a gentle slope, and then it gets steeper and steeper. So you would expect a graph of the slope to go up. And so we would have something of this shape. Now, I don't know if I'm low enough or high enough on this scale. This is just kind of a qualitative look at what the general shape would be. Certainly if I had this function explicitly and I could calculate it, I would get something that perhaps looked different, but the general shape would be the same. It would start out as positive, go through the x-axis, come around, go back up on the other side. Yes?
I'm confused as to why the slope that you just graphed does not follow the curve of the line completely. Because I don't know where that shape came from. I'm confused as to where
Okay.
it came from.
That's a good question. The slope is not going to follow the curve unless it's by coincidence. What you're really looking for is how steep is the line at that point. So one of the things that that you can do here is instead of drawing curves, you can draw this at perhaps particular values. Like we got the 0 and the both of these zeros here. So let's just look at several different places and see what the slope would be. So if I'm looking at this point right here, let's say that's where I have a fairly large positive slope. So I'll just put my value arbitrarily here as being the slope. Now at this point here I have a negative slope, and so I expect my value to be negative. And so we can just put a negative down here. In fact, that would maybe be the most negative place where we have the slope. And then looking at this other part where it's increasing again, we have a positive slope there. And so let's say if we compare it to the other positive slope, it's not quite as steep. So I'm going to put, let's say, a value that would be a little bit below what I had when it was over here. Okay, so that one is a little bit greater than that one right there. So I'm going to put this value a little bit less than that value. Okay, so it's the slope. It's not the curve itself. It's just how steep is the line, and so.
And it's based on if the slope over there is negative or positive.
Exactly.
Whether or not it dips under or not. Okay.
Exactly. So we have this general shape where it's going to be something like that. Of course, here I needed to intersect the axes. Yes.
And I'm sorry, this bothered me the first day. I cannot understand why you have the two positive slopes, and one of them is going in a negative direction, and the other one's going in a positive direction.
Okay, that's a good question. The fact that it's positive puts it on the positive side of the axis, so it's above the axis. But in the first section, as we're going from this section, the slope becomes more gentle as we get to the top. So imagine, you're climbing that hill. As you're going up at the base of it, we have a greater slope than when we're getting close to the end where it starts to taper off a little bit. Okay, so the slope up here is less than the slope down here, even though the value of the function may be greater. Let me put this into a comparison of driving a car. Okay, at the beginning, you start from a certain place and you go by milestone 1, so your distance is not very far, but you may be going at a very high rate. And as you get to mile 50, you may be slowing down, still going ahead. You would still have a positive velocity, but it could be very much less than where you started. Now, when we go from here, you see it starts out with a relatively gentle slope, and then it gets steeper as we go along, and that's why this line down here increases, is because our slope is increasing. It's not that the value of the function increases, it's that the rate of change of the function is changing, or is greater.
So if the two curves, instead of being different, were identical, would you just have to break the line so you could have both going down?
The two curves could be identical, but that would be by coincidence. Okay, there is one particular function that its slope is the value of the function. That's e to the x. But for most polynomial functions, it'll look completely different. Okay, so let me add put in just a. I'll use the board. Okay, let's say we have a plot of, let's say you're driving in a car, okay, and so I'm starting off at one point, and as I go down the road, my distance is increasing. All right, and then what I'm going to do is I'm going to slow down, and so my distance then will still be increasing, but it's not going to increase by quite as much. All right. Now, if I stop completely, my distance doesn't change, so my function, my distance here, if this is my ultimate distance, doesn't change at all. Now, if I turn around and start out rather slowly, my distance is going to decrease, but then if I accelerate, my distance is going to increase much more rapidly, like this.
You're talking about if you turn around and go back where you
Yeah, I put it in reverse. I'm not watching where I'm going. I'm just going down the street, blasting back down. Now let's look at the slope of this, what it would look like. My speed as I'm going here would be my fastest speed. So I'm just going to impose my speed as the green line here. And so we have from here to here, we're going to a constant speed, right? The slope of this line is constant, so my speed would be constant. Now, if I suddenly change, and notice I have the corner here, I'm going to be going at a slower rate, so this thing is going to drop down to, and this might, if I do it suddenly, it's not even going to be continuous. It's going to be a rate that's a little bit lower. Now, when I stop, and I'm at that same spot, I'm going to be at a zero velocity. And then if I go backwards, where my distance is declining, I'm going to have a negative slope. But then when I really gun it going backwards, then I'm going to have a more negative slope like that. Okay, so let me make this into now a curve. And I'm going to go back and forth a couple times. So I'm going to say, so I'm going ahead, I'm slowing down, I reach a point where I'm going to turn around, I start to modestly go back, and then I'm going to ultimately get back to where I started, but I'm still going backwards, so I'm going to go down the road the other direction, and I'm going to slow down a little bit, and then I'm going to turn around and speed up and get back to where I started from. So my slope here is going to look like I'm starting out with a fairly fast speed, and as I get to the point where I'm going to go, my speed has to slow down to zero because I'm going to now change my direction, so I have a negative slope until I get to where I've started. Now my biggest negative slope is right here, where I've started. So I'm going to expect that this thing reaches its peak right about here. Now when I'm turning around, when I go as far as I'm going to go, my speed is zero, and then I'm going to be going forward again with first a gentle speed and then a faster speed. And so my speed is going to look like that. And even though there's a similar shape to the curve, there's really no relationship between this value and that value, except that the rate of change that's happening right here is reflected in this number right there.
vertical.
It's always vertical, okay? So we're looking, if I go back to, let's see, if we look at this one now, first what I do is I look at the points where I'm not changing anymore. And that would be right here. That would be here. And that would be here. So at either the minimum or maximum values, those are the places that going from increasing, I'm now decreasing. So at some point, I'm not changing. I'm going forward if I'm thinking about going a distance in one direction. When I turn around, there's that instant where I'm not going forward or backwards. So those are my zeros for the derivative. Now, my slope is this, my negative slope, it's the steepest right about here. So I'm going to expect that my slope is going to have its greatest negative value, if you want to look at it that way, the absolute value of it, is going to be negative, somewhere down here, because this slope here is quite negative. And then as I come down the slope, notice I'm starting to, maybe at this point, level out a little bit, so the rate of change is slowing down. And so I may be at some constant negative, but then by the time I'm turning around, my speed has to be 0, right? I'm not going forward or backward. Now in this section here, I'm positive. And so I would expect I'm starting out with a relative, with a low rate of change. I'm going to get up to some maximum rate of change, and then I'm going to level out to no rate of change. So that part of the curve is going to look like this as well. Now for this third section, from where I'm at this peak, I'm going to start declining gently. I get to some maximum value, and then I start to taper off again. So this is going to be a graph like that, where at some point in the middle here is my maximum negative, or my least value. So once I go beyond this point of having turned around right here, okay, my slope is positive. So even though my value, and I'm sorry that I've obscured this so much, my value is negative, but I'm making a positive change. So the graph of the derivative, or the slope, will be positive, and it will increase to the point where if this is the same slope, if this turns into a straight line, then this thing will taper off and to be a large value. So my rate of change is high, but the rate of change of that particular rate isn't changing. So in other words, it's like driving down the road at a constant fast speed. My distance is changing very rapidly, but my speed may not be changing at all.
Why is it curved into the other line?
Well, it really doesn't have the same relationship. It doesn't have any relationship with that line, because if I label my y-axis properly, the curve itself may be labeled distance, but if we're talking about distance and speed, if I'm making my derivative graph, the y-axis should be in distance per time, and so the actual values of it, whether it crosses the curves or not, really doesn't really say anything, because at that point, you know, you're saying that your speed may be something like 1,000 feet per second, but you may be at 1,000 feet. You know, there's a difference in units there, and so it's a little tough because it's on the same graph. But the nice part about doing it on the same graph is that you can see what's happening to the rate of change, you know, directly. Another way to do it is to make one graph right on top of the other, and then make your X lines go from one graph to the other.
Let me see if I understand this. So if I understand this, no matter where the original curves are, at any point where the curve is going down, you always have to be on the negative side of the x-axis.
Exactly.
And the opposite, if you're going positive, just doesn't matter, like, that's what dictates where it goes.
Exactly. Imagine yourself on a cell phone with somebody driving in a car. When you ask them, how fast am I going? They can say 50 miles an hour forward or 25 miles an hour backward. It's independent of where they are. Okay, but at a certain point, you know, at the 40-mile marker, they could be going 20 miles per hour. And so at that point, the curve of the slope would be positive, even though the distance may be positive or negative or zero for that matter. Okay. So let's go on. We got the notation. When we talk about y as being a function of x, we say f at x. There's several ways to notate that. The way we're going to start out using is making it f prime. We can call that the derivative of f or f prime. Other ways to write it that we're going to find very useful are going to be dy dx, and the d there isn't a variable. It's an indication that we're talking about a small change, an infinitesimal change in y versus an infinitesimal change in x. Just like sometimes we'll see delta x over delta, or delta y over delta x, that delta means difference, and the same thing with this d that comes from the word difference. That's why we use d. And we're looking at really a ratio of the rates of change at a particular point. So if we say d at t is the distance of something at time t, then d prime is how the distance is changing with respect to the change in time, or simply the speed, right? So d is in hours, d at t is measured in miles, d prime at t is measured in miles per hour. Sorry?
So does D stand for distance?
Yeah, d here, I'm defining the function d at t as the distance as a function of time. Now, so often we'll use x as the variable and f as the function, and that's okay. That's kind of the ordinary way to do it. But if you're writing your own functions and you're making your own models and things, use letters that remind you of things. Like d is your distance. You don't have to think about that very much. T is time. It's harder to look at an x and to think time than it is to look at a t and think time. So how you define your variables, of course, is up to you, but be easy on yourself. You know, it's like if you're going to refer to yourself in an abbreviated fashion among your friends or so, you'd probably use your first initial. And that's the same thing with variables. Just use the first letter or a letter that is a little bit more useful than just plain old x, y, and z.
So that's d over dx equals d of the function?
Yeah, the derivative of the, so that's df dx. That's another way to write it. So really what we're saying here is that y is a function of x, excuse me. We've just left off the x part of it. Okay?
Is this going to be on Moodle?
I'm sorry?
Is this going to be on Moodle?
Yeah, the recording and everything, so. All right, so we went through this exercise of saying what's the height of President Obama, what does h prime mean? H at 0 is the height of him at birth. H at 40 is his height at 40. H prime at t is how fast is he growing. And so here we have an example that h prime at 7, he's not his ultimate height, but he's probably growing as fast as he ever would. Same thing with h prime at 12. I suppose that it's possible that he grows faster at 12 or faster at 7, depending on where you have that growth spurt. At h prime at 40, even though he's as tall as he's ever going to be, he's not changing anymore. So here, if we were to make a graph of his height and his rate of growth, the rate of growth graph would be at 0 while his height would be at 6 feet. Same thing with H prime at 72. He's his oldest in this list. He's at his oldest, but his rate of his height is perhaps decreasing a bit. So the rate of change of his height would be negative, even though he's much older. He's starting to shrink probably because at that age you start to lose a little bit of bone mass, and so you tend to shrink a little bit. Okay, so if we were to rank these from smallest to largest, H prime at 72 is the smallest because it's a negative number. H prime at 40 is the next, which would be 0. And then depending on when he shot up to his height through adolescence, H prime at 7 or 12 would be the greatest one. And then we're talking about temperature of a pizza taken out of the oven. So T at 0 would be when you take a pizza out of an oven. How hot is a pizza when you take it out of the oven? Anybody know? Oh, that's how hot the oven is. 350 degrees and it'd be burning, right? It'd be smoking. Not a very appetizing thing. Food out of the oven is generally 150 to 180 degrees. If you like your steaks rare, you'd probably be at 135. But that pizza is probably maybe 170. That might be a good guess. At 10 minutes, T at 10, where would you expect it to be? Yes, it would be lower. So I don't know how fast a pizza cools down in 10 minutes. It's maybe 140, 150, something like that. And then T at 120, what does that mean? That means it's temperature in 2 hours. Now at 2 hours you would expect it to be room temperature, pretty close, right? And I know what it's like to be a college student. It still tastes good then, right? The next morning, not in the refrigerator. Okay, truth be told, I still eat cold pizza too. Anyway, so now let's talk about the rate of change. T prime at T means that's the rate of change at a given time. So we would expect T prime at T to always be negative, right? Because when you take a pizza out of the oven, it's always declining. It's always cooling down until it gets to a certain value. So T prime at 10 means at 10 minutes, it's decreasing by 5 degrees a minute. So if I were to, maybe I can even do it here, draw a little graph of these things to kind of compare it to the graphs we had earlier. If I look at the temperature, you would expect the temperature to start out high and then decline to the point where it reaches room temperature. So it actually, the temperature kind of levels out to whatever room temperature is. But if I were to make, now I didn't leave myself enough room here, but if I were to make a graph of the rate of change, I'll put it right next to it. Actually, what I want to do is maybe make my axes like this, that it's going to be decreasing the greatest amount when you first take it out of the oven, and by the time it gets to in 2 hours or so, it's not changing at all anymore. So you would expect the derivative to look a little bit like that. So it's changing most rapidly when you first take it out of the oven, or it's declining most rapidly, so that's the biggest negative number, or if it's on the number line, it's the smallest number. Okay, it's the most negative number, until it gets to 0, and at some point it's just at equilibrium in the room. And you can see there's no real relationship between these two graphs from a real, what's the y value talking about, because the y value of the derivative slope here is talking about the rate of change of the first one. So it does relate to the first one, but it's talking about its change, not its actual value. All right, let's have another one of these here. So you have at an auto dealership, the revenue is in thousands of dollars when A thousands of dollars is spent on advertising. So R at A means I'm going to get whatever revenue an auto dealer gets when he spends a certain amount of, on advertising. So what do you expect R prime at A to be? What would be the units of that?
The rate at which the money he spends on advertising changes his revenue?
Yeah, so if we're talking about advertising dollars, you're talking about dollars, right? So if I put $1 against advertising, I get $1 in revenue, right? Or some value like that. So here the units almost disappear on you because the units are actually dollar per dollar. So this dealer gets X number of dollars for, or Y number of dollars for X number spent on advertising. So what do you think the dealer hopes about the sign of R prime at A? That's positive, right? That he spends more on advertising and gets more revenue. And it's possible that it could be zero, and it's possible that it could even be negative if it's really distasteful advertising, or if he's advertising that he's the highest price in town. Of course, that's going to be counterproductive, and then under those circumstances it'd be negative. But usually it's, you hope for this positive, that you're building up your brand, you're building your business. Okay, so when you have R prime at 100 equals 2, what does that mean? Well, close, but the double out, think about that a little bit more.
Or you get an extra 2,000 or something. It's increasing by 2,000?
Okay, so if our revenue is in thousands and we're spending thousands on advertising, the advertising is $100,000, and so the change would be 2. So that would imply that for every dollar that he's spent on advertising, he would get 2 in revenue. All right, so that would be, in the units there, it would be $2,000 per $1,000 spent on advertising. So when he spends it at $100,000. Now, if he only spent $1 on advertising, you can hardly get anywhere with that, right? You might put yourself in a little, want ad in the back of a paper, and that R prime may be 0 for small amounts. Or if he spends an inordinate amount of money, he could basically be getting 0 return there too, because at some value, if he spent, let's say, instead of 100,000, let's say he spent $1 million, maybe that's too much advertising and it has no impact on his revenue either. So at different levels of A, R prime can be at any particular value. So when we talk about R prime at 100 as being 0.5, what does that mean?
He's not really making, like, revenue on his advertising.
Okay, it might not be what he's satisfied with, but his revenue is still increasing, right? So if he puts $1 against advertising, let's say instead of 100,000, he puts $100,001, you would expect that his revenue would increase by $0.50 then, right? And that may not be very productive for him.
Wait, so he spends, is it okay if I just say $100?
Sure.
Since he's-
Yeah, you could say $100,
So
that's
if you
fine.
spend $100 on advertising and his R prime is 0.5, I don't understand, how much money did he make?
Well,
What was the revenue?
it doesn't, you don't know that. What you're saying is that, what is the rate of change at $100? That means if he spent a little bit more or a little bit less, what difference would it make to what he would already have? So in order to really answer your questions, you'd have to know what R at 100 is, but what R prime tells you is how would it change for small changes around that value. Okay, so it's possible that, let's say his revenue instead of 100 is, let's just pick a number, if his revenue is 500, and so if R prime at 100 is 2, that would mean that if he put in 102, no, 101, he would get $502 back.